Okay, folks. Well, it's about time to get started. Nice to see you all. Let's see, in terms of announcements, it's nice to see that our midterm didn't scare everybody away. That's great. I think we already did a good job of scaring everybody away in the first couple weeks of the semester. Hopefully we'll have that graded for you in like the coming week or so. Obviously, grading isn't a huge lift for us when the class is this size. But it does need to happen. They're currently hiding in my office somewhere. But in any event, yeah, so your remaining responsibilities are your last couple homeworks here and a final, and then you're out of here. You never have to think about numerical analysis ever again. Right, I think that's basically it for course announcements. It's nice to see everybody in costume for Halloween. Any questions, comments, concerns, things on the administrative front? Okay. In that case, we are going to continue our discussion today of multivariable large-scale optimization. In particular, let's see, in our previous lecture, we covered gradient descent, which is used for like extremely large-scale optimization, where the only thing that I can do is compute the gradient of my objective function and just basically walk downhill. But it turns out there's a number of different algorithms that can outperform gradient descent in different interesting ways. Right? And basically, all these different methods, they tend to fall into one of two buckets. There's one class of techniques called accelerated gradient descent, which has to do with sort of building up momentum. Like, so for example, if I'm walking downhill and I notice that all the gradients keep pointing in kind of the same direction, maybe it's like safer to take a bigger step. And one can show that if you do this in a really careful fashion, you can actually increase the convergence rate of gradient descent. And the other class of methods are techniques that are kind of like the Broyden's method and secant method and these other things we talked about, which attempt to do some version of Newton, right? And so you're like trying to chase after that second order convergence rate that Newton's method has. There's only one problem, which is that of course Hessian measures, these are big and unwieldy and hard to work with. So like Newton's method might be okay for small to medium scale problems. And by the way, that's certainly the case. I feel like students in 2023 often forget that like Newton's method is still valuable and not every problem out there needs to be solved with stochastic gradient descent. This is definitely not a message for your TA. But on the other hand, there's a whole series of these things that can work for different scale problems, and many of them have interesting convergence theory that can outperform gradient descent in certain cases. So first of all, we should remind ourselves what is Newton's method and how does it apply to optimization. So basically, remember the phrase Newton's method sort of, in some sense, refers to this entire class of algorithms where I take a Taylor series for the function I'm trying to optimize or find its roots or whatever, solve my problem for that Taylor series, and then iterate, right? So our first version of that was Newton's method for root finding, right, where we linearize our function, find the root of the linear thing, and iterate. Newton's method for optimization, if you think about it, like optimizing a linear function is not particularly exciting because like the minimum of a linear function is usually minus infinity, at least if you don't have constraints. So Newton's method says, aha, so what do I need to do? I need to expand two derivatives of my function, right? In other words, to write the second order Taylor series, which is exactly what we have on our screen. Yeah? And then now I can optimize this thing. Notice this is exactly the same as Newton's method for root finding on the gradient of f. So in particular, as you can see on the screen here, somebody in the internet pointed out that the screen is on my right and the box in the video has the screen on the left, but that's what you get for not going to class. Right, so in any event, I take the three-term Taylor series we have on the screen here. This thing has an optimum, yeah? So in particular, this suggests a particular algorithm for Newton's method, which is as following. We just take xk and we subtract off from this thing the Hessian of f at x k times the gradient, inverted. And this thing is the minimum of that parabola. But sadly for us, as we've already kind of talked about, this is only approximation, right? So for instance, if I'm optimizing a function in one dimension, I'll keep drawing our favorite kind of bowly function here that comes up. This thing is very clearly not a parabola. But Chris looks suspicious. It's not a parabola. No, because it's not. Okay, so right, so if like here's my xk, right? The Newton's method takes the Taylor series, which maybe like to the second order, which maybe gives me a parabola like that. This thing it turns out we know how to minimize. We're pretty good at minimizing quadratic functions. We've done it a few times in this class. So it finds this minimum point, says, aha, so this would be xk plus 1, and now I take a new second order approximation and I iterate. And all the usual drawbacks and headaches of Newton's method still apply. Like sometimes it doesn't converge, and it often converges with second order rate, but only under certain condition that we derived several lectures ago. Incidentally, one thing becomes really critical for Newton's method in multiple dimensions. I think I've never seen an implementation succeed without it, is to put a coefficient in front of this thing. In other words, you typically dampen the step size that you take for Newton's method. So the picture to keep in mind for why that's necessary is like, let's say that I have a function. Let's see if I can draw this. It's like very shallow, you know, and then who knows, like maybe it has like a giant dip like that. I think that'll do it. Right, so if I choose a point here, it could be that the parabola approximation, the minimum is like actually quite far away because it's just like a very shallow function, like the slope or the second order approximation to this point's not so good. And so that's just a reason why you want to kind of compromise between taking like a little step downhill, which is gradient descent, and going all the way to the minimum of the parabola. Now that I look at this picture, arguably I've managed to choose an inflection point, but I'm not gonna worry about that a whole lot. Yes, Harry.
So if the index is A, would you typically choose to get smaller step sizes?
That's a good question. It's actually not obvious that you should do that, right? Because once I get close to the optimum, now the Taylor series is quite good, and I really don't want to be dampening my step size in that case. So I think a more typical thing to do is to use a line search procedure. So you say, okay, I'm going to look at the line that goes through xk and through this point. So in other words, the vector in that direction. And now I'm just going to evaluate my function along that line a few times and make sure that it decreases. Right? Remember, we talked about these sufficient decrease criteria that you can kind of check. It's a good question. In fact, I don't think that you would, I don't know, actually, Chris, maybe, there's never a case, I think, where you'd want like a learning rate schedule for this thing. I think actually a fixed, unlike for gradient descent, a fixed choice of gamma is likely okay here because it already is accounting for the curvature of your function. Yeah. Notice, by the way, that this doesn't work if you don't have a second derivative, for sure. So like, for instance, like some version of the theory we did last time is perfectly fine for optimizing absolute value, but here, in fact, you tell me. So let's say that I optimize, I want to find the minimum of this function. What will Newton's method do? I mean, I do have two derivatives here. Well, it'll say, okay, I approximate with a parabola, which is this thing, and I get minus infinity, right? Like it just dies. So you actually necessarily need curvature for Newton's method to work. Okay, related to that concern, in fact, you can end up in all kinds of weird cases because, like, for instance, actually in this bad picture that I drew, take a look. Like, let's say I approximated my function here. Now what does my parabola look like? Arguably, it looks like this on the second one, but on the first one, it's certainly the case that I get a parabola that faces down, right? And now when I find the apex of my parabola, there's a fancy name for this, like the vertex of my parabola. It's like over here, which is actually farther away from my minimum. And why is that? What happened? Well, the sign of the second derivative was wrong, right? So now suddenly I'm looking for a local maximum instead of a local minimum, right? So in higher dimensions, you can end up in all kinds of weird cases, right? Like it could be that HF is like positive definite if I slide in this direction, and negative definite if I like slide in that direction. So like I'm at like some kind of saddle part of my surface. And so typically what people have to do when they implement methods like Newton's method is either convince themselves a priori that HF just is positive definite. Can anybody think of a case where that would happen? Yeah, convex functions, right? They're nice and bowl-shaped, so like these saddle cases just can't happen. Or you maybe take HF and you edit it in different ways. Actually, if you look in the physical simulation literature, you can see all kinds of really clever hacks for this. These guys are really good at this stuff, like in mechanical engineering. Here's some things that people will do. For instance, one thing you might do is before you take a Newton step, you could, for example, say, okay, well, actually what I'm going to do is use a different matrix, which is the min over H of HF minus H, maybe the spectral norm, subject to the constraint that H is positive semi-definite, right? So like I'm just going to throw away negative stuff. Does anybody happen to know the solution to this problem? Pretty close, yeah. So like if you write HF in the eigenvalue decomposition, right, then what's it going to end up being? It's going to be like the eigenvectors times the diagonal of the eigenvalues times this guy. I always confuse which one of these things is transposed, but up to transpose this, yeah. So then, oops, sorry, that is bad writing. There you go. So it turns out all you have to do to take that projection then is all you have to do is the following. Diag of max lambda k 0. This is a good homework problem for you guys to verify that this is the case. So in other words, if I want the closest semi-definite matrix to a given symmetric one, all I have to do is clip out the negative eigenvalues. Unfortunately for us, what does that mean? If I want to use this strategy for optimization, in every step now I have to compute the full spectrum of my matrix. And it turns out this thing is extremely hard to approximate. Like computing this projection actually in practice is quite hard. I wasted about 2/3 of a postdoc trying to come up with good ways to do this. One way to view this, let's say that my matrix is 1 by 1. So in other words, I'm just projecting scalars. Then like, what is the plot of my function? Well, when it's positive, it's a straight line. When it's negative, it's 0. This might remind you of a function from machine learning. This is called ReLU, and it's actually not very well approximated by any rational function, which is really a problem here. Like typically, what you want is to approximate these things with rational functions of matrices, in case you're curious, and that just is a hard thing to do. Anyway, that's far outside of the scope of this class. A different thing that you could do is say, aha, HF has a negative eigenvalue. That's bad news. I don't like that. So instead, I'm just going to do gradient descent until HF is positive again. That's perfectly reasonable. Or you might do something like take HF, that's supposed to be an F, and instead replace it with like, man, am I struggling today? I'm sorry. This isn't good because we're going to do a giant calculation in a minute. HF plus some constant times the identity matrix. You can convince yourself if C is large enough, eventually this thing will be positive definite, which is like some interpolation between gradient descent and Newton's method. These are all different strategies. Any questions? I mean, by the way, notice we haven't proved anything. Like once you do this, it's very hard to justify convergence. Like these are just different ways of like trying to make your function look a little bowl-shaped that people do in practice. Incidentally, just for fun, because I think we have a few mechanical engineers here, I'll mention one additional trick that people use for this, which is kind of clever. I really love this stuff. I can do this all day. I love these optimization algorithms. They're all really clever. They're pretty. There's so many nice things you can do. Okay. So, right. So oftentimes in mechanical engineering applications, you'll like have some, I don't know, like let's say that I make a gripper arm out of Jello, you know. So here's my arm, and now like I apply some force to it, and I want to see it bend, like that kind of thing. And typically, as we'll see in a couple weeks in this course, when we solve these things behind the scenes, we have to solve a big sequence of linear systems of equations, which have to do with like I approximate this thing with a bunch of points, and now, you know, we need to figure out the positions of these points as time advances. And very typically, what ends up happening is you divide up your domain into little pieces. So like, for instance, if you've ever taken a computer graphics class or a finite element class, you know that typically we discretize these objects as a bunch of triangles. And then what you'll do is you'll say, OK, the amount of deformation of this entire thing is roughly the sum over triangles t of some function just of the deformation of t to its like new position. Remember that as rigid as possible paper that you guys implemented in a homework? That's an example of that, right? Like you had a big sum, in that case over the vertices, but like over like local neighborhoods of like how different things squash and stretch, and then you compose them all together to get an energy. And so one thing that you can do, which is kind of clever, oftentimes, by the way, those Hessians are not positive definite. If you think about it, these problems are extremely non-convex because materials buckle, right? Like if I squash something enough, it'll like flip over the other way, which is not very convex behavior. When you want to do Newton's method in these algorithms, you end up having to like do that, or like take the Hessian of this thing. But each of these matrices is quite large. And so in practice, what folks will do is they'll take just that matrix restricted to a single triangle, so that'll be like 9 by 9, project that thing using that eigenvalue formula, and then sum them all together, rather than summing them and then projecting. So more generically speaking, let's say that I have an objective function f of x, and I say, okay, well, f of x is actually the sum over I of fi of x, right? So then what is the Hessian? Well, just by linearity, hf is the sum over I of hfi of x like that, right? Here's the thing. That projection on H is expensive, and it is not true. Like, I can't push a projection inside of the sum. That just isn't, those two things aren't equal to each other. However, that's what people do anyway, and it turns out to work extremely well in physical simulation cases. And the good news is that oftentimes the FIs only involve a few components of X, so in practice they're very small matrices. And so this is like a very common trick for projection. If you remind me on Piazza, I can send all kinds of references to computer graphics papers that do this. The cool thing is actually in mechanics, you can often write closed form formulas for the projection of the stress tensor onto these different cones. So like assembling these things becomes super efficient. Anyway, that's our discussion of Newton's method. But sadly for us, Newton's method has all the same drawbacks of Newton's method that we've already complained about. It's unstable, it can reach different weird points, and moreover, we need to compute a giant Hessian matrix that we use one time, and then we discard it forever, right? Like we compute a Hessian, we invert it, we multiply it by grad f, and then it's never useful for us again, and we move on, right? So in particular, roughly what is the time complexity of a single step of Newton? Like from a computer science time complexity perspective. Paul's saying it, but he doesn't want to say it too loud. Cubic, yeah. Why is it cubic? Because you see that -1 there, right? Like, is hiding inside of here is a linear system of equations, and like, can I use LU factorization to speed things up in this case? Not really, because after one step of Newton's method, x has changed, so hf is no longer the same. So my prefactored hf doesn't do anything. I need a new one. Yeah. So it's cubic in every single step. This is extremely expensive. Okay. This is one of these things, by the way, where like someday when you guys are all making millions of dollars in industry and I'm stuck here like grading exams, somebody's going to give you interesting plots and say, aha, I have a really great optimization algorithm, and here's my plot. The horizontal axis is iteration, like k here, and the vertical thing is objective value, like f, and like, oh my god, it goes like that, and you know, your algorithm goes like that, so like you should buy my software, right? Is this a particularly useful plot? So for example, let's say this is Newton. In fact, let's label this guy Newton. And by the way, this really is what these plots look like. And let's label this one as gradient descent. In practice, Newton is probably even pointier than that. So like, I look at this plot, like very clearly I should use Newton's method, right? Yeah, there's a different thing, which is objective and time. And these two plots are not the same, right? Because once 1k here takes cubic time, 1k here takes linear time. That's a big difference, yeah? You can do like n squared step of this for every one step of that. So that curvature better be pretty darn high before you switch to this other method. That makes sense? Okay, so in any event, for the rest of today's lecture, we're going to talk about the case where like we kind of like these Newton's method, like it converges quickly in k. The only problem is that like we keep having to recompute the Hessian, and moreover, like it might not be positive definite. There's like all kinds of headaches here. And there's a whole class of algorithms out there that try to address this in different ways. And these algorithms are typically called Quasi-Newton methods. And basically, you know, the two motivations here is grad f might be hard to compute, but hf is even harder to compute, and it's a big matrix. I might not even want to store it. And Moreover, HF might be dense. It's going to take up a lot of memory. So it's like n squared space, n cubed time to convert. These are all problems. You remember another algorithm we've already covered that had a very similar motivation? For root finding, right? That's like the only thing we've covered that's even similar, right? I know you all studied for your exam, so like there's like 3 root finding algorithms we covered. You got like a 1 in 3 chance. Rhymes with Groyden's method. Right, so we talked about, God, you guys are killing me. This is painful. Yeah, so we talked about this Broyden algorithm, and remember, that was exactly the motivation for Broyden, just with like one dimension fewer here, or one derivative fewer, rather. And indeed, one could try to design Broyden-like algorithms for, optimization rather than root finding, right? Because what did Broyden's method do? It like tried to extend secant method for root finding into a higher dimension, yeah? In general, this leads us to a whole class of different algorithms for optimization called Quasi-Newton's method. Here, the Newton stands for Newton's method, and the quasi stands for not really Newton's method. Cool? And the basic point here is that we want Newton's, we want everything, right? We want Newton's method, but we don't want to pay for it in computation, right? And obviously, we're going to end up having to give up something. We'll see what that is. So today, in the time that we have remaining, our goal is to derive an entire class of quasi-Newton methods all in one shot. I'm probably going to get this wrong, so we're going to give it a shot and see how far we get. This is actually also in your textbook. I'd encourage you to read it closely because, to my knowledge, it's not covered in other textbooks. Like, I had to write this proof myself, which means it's probably wrong. But like, essentially, when you read a lot of presentation of Newton method, of like quasi-Newton method, they like go down the list of like 12 of them. They do them one at a time. And I kind of like, I'm pretty sure you can glue them all together, but maybe not. Let's see. Okay. This is our grand unified theory. So here's going to be our assumption for today, and I think this is really carried through in most practical settings, is that you have a function and you do know its gradient. You're okay, you can at least walk downhill, but you don't want to compute its Hessian. Right? I think that's actually the motivation for almost all of the popular optimization algorithms out there right now. Okay. So here's what we're going to do in quasi-Newton algorithms, generically speaking, is we're going to do something that looks an awful lot like Newton's method, but rather than having the Hessian, we're just going to put some other matrix B. And depending on which quasi-Newton method we have in there, we're going to get a different B. Okay? And there's all kinds of different ones out there. They all have roughly the same theoretical analysis, and they all behave vastly different in practice, which is kind of interesting. And the good news, and I believe what you'll play with on your homework, but I owe Chris an email, is that you can very easily play with these things by just like flipping a switch in Python. That like it really, all of them take the same input, which is basically f and grad f, and then take different sequences of steps to get to the minimizer. Okay? So essentially, what do we need to do? We need to come up with some formulas for B, right? Okay. So in order to arrive at the vast majority of quasi-Newton methods, what we do is a trick that's very similar to Broyden's method in root finding. You guys remember the trick in Broyden's method? It basically was as follows, that like, So let's do a little bit of review, since apparently you guys are totally unwilling to speak today. I get it, it's Halloween, it's spooky season, it's a whole thing. That like, in Broyden's method, what did I want? I wanted like df, like that, right? And remember, the basic point here was that like, if I take df at some x and I multiply it by like x minus y, and they're like close enough together, or probably y minus x is a better difference. This is roughly equal to f of y minus f of x, right? And this is like a divided difference kind of thing, right? Like this is like dy dx happening here, right? And the problem is that df is a matrix, so like even if I enforce this condition as an equal sign instead of an approximation, this doesn't tell me how to compute df. It just tells me sort of one slice of df. So you remember how Broyden's method worked? It like kind of assembled df in this lazy fashion where like it kept taking the old guy and like updating it with this formula. So like this would be like xk plus 1, and then this would be xk. And conveniently, we had the f's around. This hopefully sounds familiar. You guys are like brain dead today. It's really killing me. Okay, cool. So very unsurprisingly, what we're going to do in Broyden's method is sort of just one step higher than that. Or sorry, in Quasi-Newton method. In particular, now we want products of Hessians and vectors. Yeah? But what is a Hessian? It is the derivative of the gradient. Do you guys see that? So in particular, since the Hessian is the rate of change of the gradient, if I have xk plus 1 and xk as the two iterates of my algorithm, if I multiply my approximate Hessian by this difference, then what I should get is the difference in the gradients. Because again, the Hessian matrix, like B here, is roughly d gradient dx. Does that make sense? So, what can we do? Well, we can stop here and use Broyden's method. Like, this is a perfectly reasonable way to make for an algorithm here. But actually, we can do a little better than that. That's going to be our goal. So in particular, what do we know about Hessian matrices? For one, we know that they're derivatives. But what do we know about second derivatives? Well, in particular, we know the following. We know that if I take df dx dy, this is equal to df d squared, sorry, dy dx, right? Partial derivatives commute. Incidentally, my challenge to all the math students, just because it always is to come up with like a nice intuitive picture for why this fact should be true. And I've never found a picture that like it's very easy to check this algebraically, but like it's really hard to draw a picture that is convincing. In any event, what does this imply about HF? So remember, the derivative, like the elements of HF are the second derivatives of F. Thank you, Harry. So HF transpose is equal to HF. Okay? So in our Broyden formula, we didn't actually know that, right? In fact, our DF in Broyden's method is typically not symmetric. So now what we're going to do is essentially update Broyden's method from our previous lecture and incorporate this new thing as a constraint on our Quasi-Newton matrix. That's going to be our trick. What we're going to see is this leads to much uglier mathematics. But such is life. Okay. Incidentally, another thing we know, at least if our function is convex, is that B should be positive definite. One thing we're not going to prove today, but is actually true, is that under certain conditions on F, you can actually show that the matrix you get in the Quasi-Newton algorithms that we're going to derive is positive definite, which is kind of surprising. It's just like a byproduct of convexity. But in any event, here's what we're going to do. So Broyden's method said, I'm going to take the previous B and subtract it off from our current B. So in other words, I want to take the best approximation of our previous B subject to our sort of Taylor series constraint, like the second guy here. Now I'm going to say, but I know something slightly better than that. I also know that B should be symmetric, so I'm going to add that as a constraint. These are Quasi-Newton algorithms. Does this make sense? Okay. What we're going to see is that there's actually a lot of variations of this little optimization formula that will lead to slightly different algorithms. The one we're going to derive first, this thing, as I've written it on the screen here, it's called the DFP algorithm. This is Davidon-Fletcher-Powell. And then what we're going to do is sort of swap the role of x in grad f, which is not obvious here. And then we'll derive a second algorithm, which is called BFGS. BFGS is slightly more stable in practice. OK, so this is what we need to do. Does at least the formulation here make sense of like our sort of lazy Hessian update? Yes? What was that? Oh my goodness, Harry has asked exactly the right question, which is, which norm should I use in this expression? Now, why, and so he was right to notice that I think this is the first slide in this course where there's no subscript next to the norm, so clearly something is fishy here, right? And we already have the norms on matrices, right? Remember we've talked about the spectral norm and the Frobenius norm were two examples. Unfortunately, neither of those norms actually makes any sense in this context. Let me try to explain why. So, and this is, it took me a long time to kind of understand this weird formula in these Quasi-Newton algorithms, but it actually makes sense. It's one of these things that like is usually presented as an axiom, but actually is like totally just an engineering decision. So let's say, for example, what's our favorite type of function f? How about a function f which takes the amount of water that I put into a plant and the amount of sunlight and predicts the height after 10 days. Okay? So F takes, what units of water? About centimeters cubed. Okay, what's units of light energy? Joules. I don't know if that's really the case, but in any event. So remember, this is going to be like X and Y. And then what's units of plant height? How about light years? Okay, so it's a big plant, it's true. So what are the units of the elements of H? So remember, the first guy, right, this is like df dx squared, right? So it's light years per centimeter cubed, I guess, squared. Like that, right? What are units of like the off-diagonal entries? Light years per centimeter cubed. If you're wondering, I did not write this example in the textbook. Now I can see why. Times joules. Similarly there. And then this one is light years per joule squared. That makes sense? We're using a physicist argument here. Does it make any sense to add up these entries here? No, like there's no universe where I should add together centimeters and joules, right? Or 1 over that. So think about what is the Frobenius norm, for example, of a matrix? Well, it's the trace of A transpose A, or remember there's a bunch of formulas for it, or the sum over ij of aij squared. But notice, so if I applied that to my Hessian matrix, I would be adding together things that don't make any sense to add together. Right? And that's why I think, like, if you really stand back 100 feet and look at these Quasi-Newton algorithms, they use a really weird norm. And I think there's sort of 2 reasons for that. One is just we're going to see that it's going to lead to a really elegant formula, but I'm pretty sure it would be an elegant formula in this norm too. But more importantly, we're going to use a norm where the units make sense. That's essentially all that's going on here. Now, there are a lot of norms where the unit makes sense. I mean, you could imagine that somebody just hands you a diagonal matrix that tries to equalize these things. But it's a little bit hard to do it in a canonical way if, like, the only thing I have is F. Right? Like, I want to write a piece of software that doesn't need to know your physics problem in order to choose a good norm. And so, in particular, what happens here is that they make a really clever choice of, oops, wrong way, of norms here, which is the following. Now, so, right, what am I doing? Oops, I didn't print out the right page for my notes. That's okay. So we're going to give our vectors here names. So we're going to just say that S is the difference in iterates. You can think of S as standing for search direction. Okay, and Y is the right-hand side here, the difference in gradients. I don't know what Y stands for, just stands for difference in gradients. So here's going to be the trick. We're going to take any matrix W with the property that WY equals S. Okay? And so in particular, if you kind of look here, so this is like W times something in the units of gradients equals something in the units of inputs. And one thing that you can convince yourself is that if I do that, and I compute a very specific choice of norm, that the units of every entry of this matrix are going to end up being the same. And so in particular, we're just going to write it here for safekeeping on our board. We're going to make this really clever choice. So first of all, maybe here's our optimization problem. It's like minimize over B. You can think of this as like maybe B minus B naught. Subject to B transpose equals B. And then B S equals Y, right? That's our problem after I've kind of abstracted away some pieces here. And in particular, what we're going to do is we're going to choose W so that WY equals S. It turns out any W satisfying this criterion is going to give you the same result in our theory. We're going to see that, which is kind of cool. Moreover, it's pretty easy to convince yourself that such a matrix should exist. You could either construct a rank 1 matrix really easily that just like takes Y and replaces it with S, or in the textbook, actually, there's a nice interpretation for W as sort of like a way of integrating gradients along a line, which I think is how they got to it originally. And then we're going to use a really weird norm, which is the norm of our matrix A is going to be equal to the trace of A transpose W transpose A W. Okay? If you want, we can assume W is symmetric. And in that case, what you can see is that this is roughly just the Frobenius norm of like A conjugated by the Cholesky factorization of W. So in particular, it is a norm. Have I managed to lose all you guys yet? Because I can keep trying. Okay. So even if you don't follow every single detail here, the high-level point is that we do have a degree of freedom, as Harry points out, which is we could use whatever norm we want to approximate things well in this little optimization problem for stepping our Hessian forward. We're going to choose a norm that satisfies this funny property, which essentially is just chosen as the simplest property that ensures that our units are reasonable. And when we do that, we're going to see that our algorithm takes a very elegant form. Cool? If you're like feeling lost and this is a complicated story, that's because it is. This is a nasty little class of numerical techniques. But it's actually some of the most broadly used algorithms out there in the literature. So it's funny that numerical analysis class usually skip over it because it's yucky. Okay. So our main goal for the remainder of today is to prove the grand unified theory of quasi-Newton methods, which is to say, we're going to derive the following proposition, which, if you stand back 100 feet from the different methods we'll cover, are all covered as special cases of this thing. So here's what it says. Let's say that I take a matrix BW, and I'm going to, B naught rather, and I want to approximate it with another matrix B, right? So this would be like the previous Hessian and the next Hessian in my algorithm. And now I add two constraints on B, that it's symmetric, and that B times S is equal to Y, okay? Moreover, we can assume that B naught is also symmetric, right? Because like if I'm running my algorithm, if it starts symmetric, it'll just kind of stay that way. Yeah? Here's what we're going to find is if I take the minimizer of this optimization problem, so long as WY equals S, then I'm going to get the formula at the bottom of the slide for B. Notice this is a really nice formula. What it says is I take B, I just pre and post multiply it by some very simple matrix, and then I add to it a positive definite thing in Y. Now, if you guys have like a clever interpretation of this formula, that's fantastic. I don't. But the good news is that it's closed form, right? It's a formula. So basically what it says, notice that now if we want to implement this DFP algorithm, it's very simple, right? Like I have this Hessian. I take a step of my optimization by doing Hessian inverse times gradient. And now I use this formula to update my Hessian, and I just go back and forth between those two things. Cool? This is heavy because it is. Okay, so our goal is to prove proposition 9.3. Once we have this, we're cooking with gas, okay? So, the first thing that I want to do, like kind of continuing our discussion, is like this W norm is kind of annoying. So let's just get rid of it. And it's actually this initial step, which is what sort of justifies this choice of WY equals S, okay? So here's what we're going to do. This is fun. By the way, we're going to assume that maybe W transpose equals W, and W is positive semi-definite. Otherwise, you don't have a norm. Okay. So what can we do? We're going to use all of our favorite tools. By the way, when we do conjugate gradients next time, we're also going to use all our favorite tools. What do we do to positive definite things as S955 students? We only know how to do one thing. Cholesky, thank you. So in particular, I can factor W equals LL transpose. Yeah? And here's the reason I'm going to do that, is that I'm going to kind of plug that into this norm formula and then do a change of variables that just replaces W with the identity. That's going to be our first step. Okay? So here's what we're going to do. So now let's define a matrix D, which is going to be equal to L transpose B minus B naught times L. So basically, we're just gonna, because like we're gonna actually do two things at the same time. We're gonna replace b minus b naught with just like the norm of a matrix, and we're gonna get rid of w, right? So that's kind of what's going on here, right? So in particular, then, we have a formula for b, right? This is b is equal to b naught plus L inverse transpose times d L minus 1, right? So this is just a rearrangement of that expression there. You guys see that? Okay. Whew. So now, what do we have to do? So we have to do kind of two things. We need to figure out a new expression for our objective function and then our two constraints, right? So first of all, notice if b is symmetric, then d is certainly symmetric as well, right? Assuming b naught is. Yeah, vice versa. So great. So this first constraint is like going to be kind of easy to deal with. But the second one's kind of annoying. So bs is equal to y, right? That's our constraint. Now let's plug in a lot of nasty stuff. So in particular, we have an expression for b. So this is b naught plus L minus transpose d L inverse times s is equal to y. Right? So that's constraint number 2 here. Everybody with me so far? So I just took this expression and I plugged it into this constraint. Okay, so let's do a little bit of rearranging on this thing. So what is our unknown here? It's actually only d. You see that? Everything else we actually know. Yeah? So in particular, we can rearrange. So we're going to have d times L inverse times s is equal to L transpose times y minus b naught s, right? So here's y minus b naught s, and then I have an L transpose to get rid of the thing on the left-hand side, and that's to get this expression here. Everybody follows? You can see this is just ugly. Like, that's just life in the city. I'm going to keep saying that because like I'm uncomfortable with this, and I want you to be too, so you're paying attention. Okay, so now we're just going to do lazy mathematician thing, which is we're just going to give things names and then never think about them again. Okay, so L inverse S, let's call this W. Cool? This giant ugly thing here, I don't know what it is, but it's something that I can certainly compute in terms of the inputs to my problem. So let's give this thing a name. Let's call it Z. Z if you're British or Canadian. Okay. So this is pretty nice, because now we have a beautiful expression. dw equals c. See, what's so bad about that? That's our point. That basically, this constraint bs equals y is equal to a constraint on this new matrix I've defined d. And like, sure, the ingredients of the constraint are kind of ugly, but I can just factor them away, and then what's left is just linear again. Okay? So, great. Now we have a translation of that guy. Okay? So, there was one glorious semester where I taught in this classroom that had a little button that swapped these. Yes? Nope, exactly the same W. It's any symmetric positive definite W that satisfies WY equals S. Yep. And I claim that those are the only conditions we'll use. And if you look in the textbook, you'll even see a little exercise that like gives you a formula for W and shows that like gives you an example of a W that for which this is true. Okay. So what do we need to do? Well, the next thing we need to do is to work out our actual norm here. Do we want to do this, or do I want to tell you to just trust me? We'll just do it. Okay. So we need the norm of b minus b naught w, maybe squared just for convenience. Yeah? Now, first of all, what is b minus b naught? It is the norm of L inverse transpose d L inverse w, like that. Right? This is from this expression up here. This is actually just the definition of d. Cool? So now, this is equal to, oh, don't make me do this. It's fine. Okay, so it's equal to the transpose of this, so L inverse transpose D transpose L inverse transpose times W transpose times this thing again, L inverse transpose L, or D L minus 1 times W again. Did I manage to do that right? I think I did. This guy. Probably. Let's see. So it should be the transpose of this matrix, right? So it should be L inverse transpose, D transpose, L, you're right, negative 1. Ah, no. Negative 1. Okay, thank you. Okay. Now what is W transpose? Remember, W is equal to LL transpose, so W transpose is equal to also LL transpose, because it's symmetric. Okay, so there's an LL transpose here, and there's an LL transpose there. And now finally, we can do a lot of cancellation. Do you guys see that? So we have an L inverse and an L. Gone. We've got an L transpose and an L inverse transpose. Gone. We've got an L inverse and an L. We have an L transpose. Remember that I can cycle around traces. So this L transpose and that L inverse transpose are gone. So at the end of the day, when the smoke clears, we have that this is the trace of D transpose D. Everything else went away. Sneaky, huh? That's why we chose this little substitution. So this thing in particular is just the 2 norm squared, or Frobenius norm, rather. Isn't that cool? So we just did 2 things at once. We got rid of B minus B naught, like now we're just optimizing for like a delta. And also we did a change of coordinates to change the W to identity. If you're wondering, I didn't guess this correctly in the first try. Like that's why I gave you this kind of, okay, not like super clever, but like carefully chosen formula for D. Okay? Okay, so now after our optimization problem is converted here, we can finally write our problem here. So it's the min now over matrices D. I'm going to put a 1/2 here just for fun. So this is 1/2 the Frobenius norm of D. That's what I've written here. Subject to 2 constraints. D transpose D is equal to, sorry, D is wrong lecture. D is equal to D transpose. And moreover, dW equals Z. Right, so notice if I can solve this problem for D, I can do this substitution up here, and then I've solved the problem for our original B. Everybody with me so far? I know this is ugly, but it's slightly less ugly than what we started with. Okay. Notice, by the way, I mean, this was unnecessary. Like, we could have just done a million calculations on the original problem, but like the formula is already kind of horrendous, so I think it makes sense to like try and change coordinates to something that like is slightly less of a headache. Okay. Whew. So basically, our remaining task in the next 30 minutes is to come up with a closed form formula for the D that solves this optimization problem. So, what are we to do? We have least squares, a linear constraint. What's probably the strategy? We actually kind of only know one strategy for deriving formulas for minimizers of constraint problems. Lagrange, thank you, Paul. Okay, so in particular, the Lagrangian of this thing, what's it equal to? Well, we've got, we need to give Lagrange multipliers. So let's make a Lagrange multiplier A for this constraint and one lambda, I think I called it in my notes. Lambda for the second constraint. Remember, so what does the Lagrangian look like? So it's hopefully you guys are like slowly getting used to this calculation because we've done it approximately 1 billion times. So it's the sum of the objective function and then like the dot products between the Lagrange multipliers and the constraints. Notice this is a matrix constraint, so the Lagrange multiplier here actually has to be a matrix. You have to be a little careful. Okay? So this thing is equal to 1/2 the trace of D transpose D plus we need the dot product between A and D transpose minus D, which we can write as follows. This is the trace of A transpose d transpose minus d, like that. In fact, just because I know the second that I diverge from my notes, I'm going to start making mistakes. Obviously, I can put the transpose on either one of these d's. I'm going to put it there. Either one of these would work. I just want to make my signs and my notes align. Okay? And then we have plus the dot product between lambda and dw minus z. Right? So any minimizer of this thing has to be a critical point of this weird function. Yeah? A few nods. That's good. You guys are slowly waking up here. That's great. I think like once we start going to things that look like least squares, then we're like kind of on board again, which is good. Okay. So sadly for us, we need to take the gradient of this ugly thing. So the gradient with respect to lambda and a is easy enough. That just gives us the constraints back. Or yeah. So then the gradient we really need, is the gradient with respect to d. Okay. So we have 0 is equal to the gradient with respect to d of our Lagrangian. So what's the gradient with respect to d of this thing? Remember, this is the 1/2 of the norm of d squared. That's what this is just fancy notation for. So what is the gradient of this thing? We've seen this many times. It's just d. Yeah. Right? This is like 1/2 x squared. So the gradient of that is just x. Now, the other two, you can either work through the indices, or you can go to my favorite website, which is matrixcalculus.org. Both of those are going to tell you the same thing, I hope. Which is, first of all, notice that this expression here, if I differentiate with respect to a, it's just going to be the constraint, right? That's all that's left. Like this is the dot product between a and smaller stuff. Similarly, right, I could flip the roles of a and d here. And what I'm going to get is a minus a transpose. Okay. And then we're going to get plus lambda w transpose. You kind of see that because there's like a d here, so it's like lambda transpose dw. And so if you kind of work through the indices, you'll find that this is the gradient. Okay? Slowly, our task is becoming more clear, right? We started with this optimization problem. Our task now is to just find formulas for a and lambda and w. Okay. You guys are so quiet that I can only assume I'm not moving fast enough, and I should write even more formulas. Okay. Is it okay if I erase this stuff? Yeah, this is like old memories. I'm tempted to keep it only because we're going to need to undo some of our substitutions, but I'll remind you of that when we get to it. Okay. Whew. Okay. So we don't know a whole lot, but let's make a definition. So in particular, in this expression here, we have a minus a transpose, which is kind of annoying to work with. So let's give it a name. Let's call Q a just to match my notes, a transpose minus a. Okay? This is just a new matrix. Cool. Notice, by the way, that there's actually no additional conditions on a. So a is kind of underdetermined from this setup, which is why we kind of know that Q is going to be enough. But that's not going to end up mattering, but like just an FYI. Okay. So Q is equal to A transpose minus A. Then it's very easy to see that Q transpose, well, what's Q transpose? It's equal to A minus A transpose, which is just minus Q. Okay? So Q is almost symmetric. Right? So I transpose Q and I get minus Q. Does anybody know the name for this kind of a matrix? The opposite of symmetric. Anti-symmetric. Yeah, or skew-symmetric. That's fine too. Yeah, so this is an anti-symmetric matrix. Or if you're, below the equator, it's skew-symmetric. Okay, so, right, so this is Q. So in particular, we now know, just by substituting that into our Lagrange multiplier expression, that 0 is E equal to Q plus lambda W transpose, and moreover, Q transpose equal to minus Q. So now we're starting to like get simpler and simpler expressions. Notice my strategy here is that like I don't like ugly math, so I just keep making more and more substitutions until I get a really short formula. Okay, so now we have to do some annoying stuff. So here's a kind of fun fact. We know that Q is anti-symmetric. What do we know about D. Oh, oops, that's not a 0. I'm sorry, that's a D. Yeah. Right, so here we moved everything to the other side to get D. Oh no, wait, is there a... oh no, there's a minor mistake. Boo, there's a sign mistake in my notes. Okay, this is how it starts. We can put a minus here. And Chris is going to remind me at the end of the lecture to fix this in the textbook. I'm so sorry to do this. I hate it when professors do this. They go back and they realize their notes are wrong, and then they have to fix something a little bit. Here's why I'm going to do that. Now this becomes a minus, and then this becomes a plus. Okay? And Chris is going to remind me or send me an email right now to fix the sign. Okay. I apologize. This is the first offering of this course. This is what happens. Okay. Now we're good. So, to get back on track, we know that Q is antisymmetric. We also know that D is symmetric. So we're going to combine those two facts and do something really sneaky. So in particular, one fun fact about a symmetric matrix is that if I average it with its transpose, what do I get? I get the same thing back, right? So in particular, D is equal to 1/2 D plus B transpose, right? Because secretly these are just two formulas for D. But why should I do that? Well, this is going to be equal to 1/2 D, which is going to be like lambda W transpose plus Q. But then you're going to have plus Q transpose. And remember that that sum is 0. So like that. Cool? First of all, we already learned something really good about D. D is the sum of two rank 1 matrices. Now we're cooking with gas. You see that? We just learned a really profound fact about our optimum point by just doing lots of munding around. Okay. So right. So now we're starting to get somewhere. So now we also know that dW is equal to Z. Notice our strategy here. Like we're basically just going through our constraints and plugging them in. Like this is our constraint that D is symmetric. Now let's use the dW equals Z. So let's say Z is equal to dW. Or for convenience, I'm going to put a 2 on both sides. We'll see why in a minute. What is 2dW? Well, 2d is equal to lambda W transpose plus W lambda transpose. Times W. Cool? So this is just plugging this expression in. Okay. And conveniently for us, we can simplify this. So W transpose times W is the norm of W squared. Yeah? So this is the norm of W squared times lambda plus, this is really just the dot product of lambda and W, right? Times W. Cool? Notice that we've like basically taken Z and written it in lambda comma W coordinates here. It's kind of nice. Okay. You guys don't seem to agree that it's as nice as I think. I think it's great. This is very cool. Okay, so now what we're going to do is we're going to take dot product on both sides of this expression with W. The reason, why are we trying to do that? Like eventually our goal here is going to be to isolate lambda. Where's lambda? Here's lambda, right? And so we're going to kind of do that to like, essentially we're going to get an expression for this lambda dot W here by taking dot product with W. So you're going to end up with the lambda dot W in the first term too, which seems kind of nice. And then we're going to plug it back in here to eliminate lambda. That's our strategy. Okay, so we take a dot product with both sides of W. What are we going to get? We're going to get 2Z dot W. This thing is equal to, well, you're going to have mod W squared times lambda dot W plus W dot W, right? So that's W squared again times lambda dot W. Isn't that kind of cute? So notice that when I take the dot product to the right-hand side with W, I have lambda dot W times norm of W squared, lambda dot W, norm of W squared. Really pretty, right? So this is equal to 2 lambda dot W, norm of W squared. Now we're getting somewhere. Like these expressions just keep getting cleaner and cleaner and cleaner. Now we're down to one dimension. Okay, so. Sadly, I have to erase. I'm sorry, I wish this classroom had more blackboards. Rarely in this course do we end up using them all, but today is one of those days. Oh boy, I'm going to be sneezing all night. So in particular, what we can do is go back to our expression here. We have, remember, it's just 2z is equal to mod w squared times lambda plus lambda dot w times w. But now we can actually have an expression for lambda dot w, right? It's 2z dot, or z dot w divided by w squared, right? So in particular, this is times lambda plus, and now let's eliminate this guy. This is z dot w over w squared, all of this times w. As a side note, we're like dividing by some stuff, which is something you should be careful about in a real proof. You can go back and kind of convince yourself that none of these vectors is equal to 0 in an interesting case. Everybody see how we got here? Any questions so far? A lot of algebra. Here's something really cool. Remember, our goal was to isolate lambda, and now it's only in one place. That's why we went to all this effort. So in particular, we find that lambda is equal to 1 over the norm of w squared times 2z minus z dot w over w squared. Okay, times w. Okay, or we can expand that, of course. This is equal to 2z over w squared minus z dot w over w to the fourth times w. Okay, now we go to page 2. Okay, but this is great actually because again, remember, like, what is our optimization problem? I should remind you of it here. It's to minimize the norm of d squared subject to d transpose equals d and dw equals z, right? That was our problem you might have forgotten after all this algebra. This is the problem we were trying to solve. But take a look. So we now have a formula for lambda involving z and w, but those are actually inputs to our problem. So we're good. We just wrote a formula for lambda. Yeah? Yeah. Okay. So we have to do one more ugly thing. I keep saying that. Remember that we have this expression, right? Remember from the d equals 1/2 d plus d transpose thing? We know that d is equal to 1/2 lambda w transpose plus w lambda transpose, like that. Okay? Now we have a formula for lambda, so guess what we're going to do? We're just going to plug it in and suffer. Okay, so in particular, this is equal to 1/2 times lambda w transpose, but here we've got that lambda is equal to 2z over mod w squared minus z dot w over w to the fourth. All of that times w transpose plus w times this thing transpose, 2z over w squared minus z dot w over w to the fourth, like that. Oh, oops, there should be a w here. Right, so all I did was take this formula for lambda and plug it into that expression up there. And so finally, if we rearrange this thing a tiny bit, notice that, like, we have two terms that end up with a 1 over w squared factor, and then we have two terms with a 1 over w to the fourth factor. So we're going to kind of group that way. And what we'll get is the following. So we have 1 over mod w squared. Okay. And what are we going to end up with? We got a 1/2 and a 2 that cancel. Then you have z w transpose plus wz transpose. Nope, that's, oh, sorry. We're doing the squared ones. So you have z w transpose plus wz transpose. Like that. Okay. And now we need to do the cortex stuff. So now we have, as Paul points out, minus z dot w over mod w to the 4th. And each one of these things is just w transpose. That's actually it. We're done. So let's stand back 100%. Like, I think it's so easy to do this calculation. Finally, you step back and say, wait a second. So take a look. We now have a formula for D, right? What is D in terms of? It's in terms of W and Z, which are exactly the inputs to our problem. Yeah? So great. So what did we show? That we showed that essentially D is equal to the sum of 3 things, right? I believe D ends up being rank 2, if you kind of think about it, because the column space is spanned by Z and W. And that's basically it. So now our final step of our proof, which I think we can possibly omit. We can take a vote in this class whether you want your instructor to continue going through excruciating pain. I'm happy to. I got all the time in the world. Is we now have this expression for D. What's our last step got to be? Well, if we look at our statement of our theorem, do we want D? No, we wanted B. Remember what B is. B is equal to B naught plus L inverse transpose D L minus 1, right? So what do? We plug this expression in here, and then we just start simplifying the bejesus out of that expression. Let's take a vote. How many of us want our instructor to actually simplify? It's fine. It's like I have a chalk allergy. I'll just be tired tonight. I didn't have Halloween plans anyway. Okay, great. That's what I was hoping the response would be. But essentially, if you plug this in and you do a lot of simplification, the expression you will get is precisely the one at the bottom of the slide here. I think this is not entirely surprising. Notice it has like kind of a similar form. If you multiply out this product, you're going to end up with like kind of a low rank change to B naught, which is exactly what you would expect. Okay? But this is certainly the idea of the proof. It's actually, in a sense, it's ugly, but it's straightforward. Like, it's all we did was Lagrange multipliers and then just a ton of algebra until we could isolate D, which is really just B in disguise. Any questions? And by the way, even if you totally forget the proof here, that's okay. What matters is this nice formula here. Right? So again, to summarize, what did we do? We said we take a matrix B naught, and we want to edit it. So we're going to come up with a new matrix B with 2 constraints. One is that B has to stay symmetric. And the other is that we know what B looks like along one-dimensional axis, like BS equals Y. When we do that, this is necessarily the closed form of B. So here's our algorithm for optimization. It's actually really easy to implement. Here's the thing. It feels really ugly, because it is. And if you get one letter wrong in your code, it will just fail and diverge. I'm tempted to put it on your homework just so you can suffer the pain of implementing yucky numerical algorithms, but I think we'll skip that. So here's the thing. There's just an update for B. That's really it. So like your algorithm, all it does is it takes a step, right? So it does like a Newton step. Remember what that is. It's like B inverse times gradient. And then remember that Y and S are just the difference between iterates and the difference between gradients. So I update those, and then I use this formula to update B. And then I iterate. What's the complexity of this algorithm? It's actually still cubic. We actually didn't gain anything at all. Do you guys see that? So we now are no longer using the Hessian, so we don't have to worry about the complexity of evaluating H, but we still have to invert B, right? So we didn't actually gain a whole lot beyond not having to evaluate the Hessian of F. Does that make sense? Well, funny you should ask. So there's a second proposition, which thankfully we do not have time to prove in lecture today. which is that if I have a matrix B, which can be written in this form, its inverse is necessarily the expression at the bottom of the slide here. The proof of this expression is actually extremely easy. What you do is you take B and B inverse and multiply them together and show that you get identity. Like it's really like it's one of these proofs that like it just requires more grinding. It's just like exactly what we did on the board here, just even more of that. Yeah. But essentially the basic point here, which is by the way exactly the same trick we used in Broyden's algorithm, is that like if we can have this nice formula for how to update B, we can also have this nice formula for how to update B inverse. Incidentally, if you guys take a parallel computing class, like you get really excited about really, really fast numerical linear algebra, these kinds of formulas are actually sort of a theme in that universe, where their basic point is that there's this huge class of methods where I'd make these like little low-rank changes to matrices, and then I want to know how different pieces of the linear algebra puzzle change in response to that. So like this is a way to talk about updates to the inverse of a symmetric matrix. You can also talk about like if I add a rank 1 change to a matrix, what happens to its Cholesky decomposition. That's a really nice one. And that's sort of the beginning of these really parallel, sparse, fancy algorithms for numerical linear algebra. So this is like the tip of a very large iceberg, which is why I think it's worth covering. And the proofs of these things are really just grinding. Like there's really not much more to it. They're all different variations of that one formula we saw in the Broyden lecture. Okay, so this algorithm is called Davidon-Fletcher-Powell. By the way, all these algorithms like have a bunch of people's names attached to them. It's like an interesting 1960s phenomenon. Like I kind of wonder if it's tied up with like, you know, the atomic bomb and all that stuff. There were a lot of like physicists with big personalities at that time, and it is very interesting to see like all the algorithms from that period, people like named after themselves, which is a little different than most numerical methods. It turns out DFP works kind of well, and it does indeed involve, you know, avoid inverting matrices if you use this update here, right? Notice this is now quadratic time. However, it can actually be a little bit unstable, and there's a reason for that. If we look at the optimization problem for the Broyden update, this terrible formula that we derived, it wants B to change as little as possible, right? Like that's really what's going on in this optimization problem. But do we use B in Newton's method? No, we use B inverse. B inverse could change a lot. Does that make sense? So like for instance, 0.1 and 0.00001 are very close together, but their inverses are very far apart. And so this is, that sort of intuition can sort of give you a toehold into seeing that like sometimes this algorithm can be quite unstable. And so a couple years later, actually 4 different people in some set of subsets, I don't know if they were pairs or individuals or what, all proposed a slight variation of the DFP algorithm, which is the following. DFP algorithm is sort of derived in 2 steps, one of which we did carefully and the other of which we're skipping, right? Which is first we prove this formula here, and then we show that there's like a formula for the update of the inverse. But here's kind of an interesting thought, and this is such a clever idea. This is just so cool what these people thought about. Like maybe what I really should be doing is like let's come up with another matrix. Let's give it a name. You know, so here's our observation so far, right? Like basically just because the difference in B's is small does not mean the difference between their inverses is small. So here's an idea. Let's just change our optimization problem. In particular, let's optimize instead for BK inverse directly. Yeah? So let's say we call C equal to CK equal to BK inverse. Yeah? So remember, we added this constraint on B, right? We said BS is equal to Y, right? So in other words, CY is equal to S. Hopefully, even if you didn't follow any of the rest of the lecture, you do believe this. So now, here's a really clever algorithm. This is called the BFGS algorithm, and it is the most common choice for large-scale or medium-scale optimization before you get to like stochastic gradient descent. And it does the following. It says, I'm going to optimize not the difference in B's, but rather the difference in their inverses, and say their inverses should change in a small amount. The inverses are still symmetric matrices, and now I'm just going to take this condition, I'm going to replace it with that one. You have to be a little bit careful. Your W becomes a W prime that satisfies the opposite condition on W, because we're working with inverses now. But essentially, that's the only difference between DFP and BFGS. DFP says I want the Hessians to not change very much. BFGS says I want the inverses of my Hessians to not change very much. These are different optimization problems. They both have the same order of convergence theoretically, but this one tends to be a little bit more stable, so this is the choice that almost everybody uses in practice. Like if you download the SciPy optimization library and you give it a function and a gradient, you just take the default, this is probably what it's doing. So just FYI, like in the computer graphics literature, this is what everybody uses. What's up?
Is there a time you'd prefer the other one?
DFP is a good question. I think it's very rare. I actually have never encountered a place where it gets used. I think oftentimes what people do in practice is like, all of these algorithms are just like twiddlings of about 5 lines of code. So people will just try them all and then just empirically kind of see which one gets there fastest. But I don't know if there's careful methodology there. It's a good question. The good news is that, like, why did we go to all the work to prove this like ugly lemma here? Well, notice that like this lemma still applies. We just swap the roles of S and Y. Right? So if you go into most textbooks, for some reason they start over and derive it a second time. But actually, it's perfectly fine to apply exactly the same formula. And what you get is just, this formula for BFGS, which is essentially this thing. But now you no longer have to invert C, right? C is already the inverse of the Hessian. Cool, huh? So the difference between BFGS and DFP is just a difference between this update for C and this one, right? Like that's it. They're just different formulas in terms of Y-ness. Right. So the good news now is we've now got down to quadratic time. We can actually get down to linear time. And this is really the algorithm that people do. And this is just like we talked about for Broyden's method. There's a technique out there called LBFGS. Almost all engineering students, like they you know, if they've touched optimization software, they like use this phrase all the time and have no understanding of what it is. But really, LBFGS is just the BFGS algorithm, where at every step I build up C by just keeping track of the last like K iterates, or L iterates, I guess, rather than the full thing. Right? And as we kind of argued for the Broyden's method, you can store C not by like an n by n matrix, but rather just like the sequence of the last few iterates, and then build it up on the fly when you need it. Right? That's the basic trick. Implementation of this algorithm is annoying, but lucky for you, almost any standard optimization library does it for you. So it's very rare to actually have to code this up in practice. So now you guys are basically up to date with state-of-the-art for medium scale optimization. And then for large scale stuff, typically we move on to like stochastic gradient descent and those kinds of tools, which we've touched on. And we might come back to later in this course, depending on how much time we have left. But that's our basic optimization story. So to summarize, like we have, for extremely small problems, you know, we can do Newton's method, or extremely small, we can even do golden section search, right? Then we moved on to gradient descent, which is like a nice, stable, easy to implement method, but the convergence rate is slower. Then we have Newton's method, where the convergence rate is faster in K, but the matrix is hard to construct and the invert. So now these quasi-Newton methods try to approximate our Hessian, or its inverse, using these different update strategies that we've already kind of seen. Okay? All of these algorithms are totally generic, right? All they want is just like differentiable objective function. And like notice that like usually the way that you implement these things is that they take a function pointer to f and its gradient. So like the code is sort of like meta code that takes in a function that evaluates the gradient when you need it. Because like sort of the form of the gradient doesn't matter for any of these techniques. Does that make sense? In the next couple lectures, just as a preview, what we're going to cover are now algorithms where we're going to like pull apart Newton's method. And we're going to say like, what if the, like for example, something that we've already studied in this course is like, what if really the only objective I really care about is this? I don't need my algorithm to work on a very generic thing because all I ever want to do is solve least squares, right? Well, now we can pick apart the steps of Newton's method specifically for this function and ask whether we can come up with more efficient algorithms that leverage the fact that we know the form of the gradient and the Hessian, right? And that's going to lead us to a set of algorithms called conjugate gradient methods, which is what we'll cover next time. Then, what we'll cover the time after that is like, let's say that I want to solve problems that look like that, but maybe have other terms that are nonlinear, but it's always the same nonlinear term. It's not like I want to solve that plus like cosine. It's always the sum of these two things. Now can I kind of edit my linear algorithm to account for simple terms like this, and that's going to lead us to things like proximal algorithms. Okay, so that's our plan for the next 2-3 lectures, depending on time. And then we're going to throw all this stuff away and do differential equations. So if you need a reset in this class, that's a good time to like get back on board. Okay, fantastic. So with that, everybody do your homework, and I will see you on Thursday. Have a lovely Halloween. Don't do your homework tonight. Go trick-or-treating. And yeah, I'll see you later in the week.